Length. It's what rulers measure. What happens when the unit we're looking to measure is far frickin' smaller than anything we can really conceive of? Well, he's playing with circles again. You all know what this means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. Yes, we're back. What's our friend over here? Well, this happens to be a quick screenshot out of Thad's book, 44 Derangements, and the Balance of Persistence. You can get it on Amazon if you really want or something. I just linked down to the video and everything there. But let's take a quick look. So this is several pages ahead from where we were the other day. Okay. So what we talking? Oh, so we started with chapter 1. I think there was a chapter 0. The book coincidentally just happened to be 137 pages. The little things in life. Speaking of little things, the Planck lane. So let's embiggen it. There we go. All right. So I got all these circles here. Let's read. Chapter 3. The next limit. The break in scale symmetry between the first and second scales of any planar circular construction is blue B equal to 7. Basically, you can have a circle. How many equal size circles can you put inside? 7. That's 5 plus 2. Pretty neat. This follows from the fact that on our planar circular construction, when we are constructing things from circles, the next circle available is composed of 7 circles, 6 outer circles surrounded by a 1 inner circle, and a negative space that divides them. As you can see, number of circles is the second scale. This is what we're claiming as length. So basically, time is basically that center circle. It would be the minimal turtle of our particular construction, some may say. Number of circles included in the first scale, 1. How many included in the second? 7. So that's why we have red n, set to 5, the dimensional ingredients, if you would, of our minimal arena here. And B is the break in scale symmetry. So that's why when you see it's in a round, and that goes into derivations, including the next one we're going to do here. Let us continue. With this in mind, let's zoom out to the next partition limit of the minimal arena. Balance 1, because time was balance 0, whose interaction is the operationally rotated inverse action of balance 0, adjusted for the break in scale symmetry between them. The balance maintains a new external rotation, theta of 1, that rotates cycles through d of 1, which equals the break in scale symmetry b times n, which is the 5-dimensional ingredients, which leads to 35 of the 44 fundamental derangements. So basically, since time is basically our base, consider it the foundation that we're building up upon. And by up, it appears to go like bigger and bigger and bigger. It's almost kind of fractally in a way. It's very interesting. But as we can see here, so basically your base time, you have 44 actions. You have 5 ingredients, move them around in 44 different permutations, if you would. Okay. So we're going to take a large amount of those actions, not all of them, using this construction here. And we're going to arrange them in a particular way. That happens to be 35 ways you can derange things. Excuse me. Yeah, possible permutations. So when we take this equation here, this is the hyperbolic sine of the, excuse me, the hyperbolic sine times the hyperbolic sine of 1 divided by break in scale symmetry, which is 7. We end up closing the arguments. We raise it to the -1, and the same before, we multiply it by e, the base of natural logarithms. And we raise it to our theta of 1, that's our x, and we set it equal to the number of derangements there, which would be the 35, the 7 times 5 there. So that gives us the theta of 1, which is set equal to 1.6162918175645 dot dot dot. Since it's a geometric action, we can continue as many digits as we want. And that equals the hyperbolic sine function, which equals to b. Okay, and we're just going over the things there. All right, that was cool. We don't need you. All right then. But hey, welcome, Whitechapel. Thank you for joining, my friend. We're going on our Planckian journey. If I'm just going to do one of them each 5 days, because now I actually slowly developing some Wolfram cantrips. I have some semblance of what the heck I'm doing, so things are becoming much easier on that side. But what the heck is the Planck length? We went into the Planck time a wee bit yesterday, so let's do our due diligence. Okay, this is from the simple Wikipedia.org. Okay, the Planck length, L sub p, is an extremely small unit of length. It is calculated from 3 physical constants: the speed of light, the Planck constant, and the gravitational constant. It's kind of like the Planck time yesterday. Why is it there having to be, like, I don't know, 3 or 4 constants you can use to derive these things? It's pretty neat. The length was established as a way to simplify many of the more fundamental equations. To write down the equations in Planck units, you can do away with many physical constants and not have to worry about dimensions. The Planck length does not have any precise physical significance, and is a common misconception as the inherent pixel size of the universe. Yeah, in my mind, I kind of picturing a 3D-ish TV there. That's just me. And there's things happening. There's bodies. There's stuff doing things and things doing stuff. It's about 1.616255 times 10 to the -35 meters, or about 10 to the -20 times the size of a proton. Okay, so basically, if you got a proton, that's freaking small. Now go down another 20 orders of magnitude. That's redonkulously freaking small. I think it's been a while since I used that word. I like that. As one of the Planck units defined by Max Planck is important length for quantum gravity because it may be approximately the size of the smallest black hole. Well, coincidentally, if you take the Planck mass, it's about 10 to the -8 kilograms. Really small, but about the mass of, what is it, human eyelash, a flea egg, something like that. It's something that we can actually try to conceptualize. This, it's like, now I'm not saying this is why Einstein may have been able to kind of literally blend space and time, because we're talking about 10 to the -44 and 10 to the, what is it, -35. Yeah, that's like, I don't know, 15 to 20 plus units. Small, actually, no, for both of them, 20 plus units of orders of magnitude smaller than we can actually observe. GR seems to be doing pretty well. But welcome, Courtney. Thank you for joining us, my friend. We're just talking about like the minimal, like the smallest thing, because you always think like, was it Zeno's paradox? You have something. We have cake. Cut the cake in half. We take that half of cake. We cut the cake again. And you keep on cutting the cake, and you're like, oh, we just do this forever. However, when you get down small enough, basically there ain't going to be cake no more. You might have some frosting. Maybe there'll be a crumb. And then you'll actually get down to the molecules. And then you'll get down to the individual atoms. If you start splicing the atom up even more and more and more, basically you get 20 orders of magnitude smaller than like a proton. And that's the Planck length. It seems like magic. Can neither confirm nor deny it. But all right, let's just pop over to the full wiki over here. Is it updating? Oh no, I did the wrong thing. Oh my god, I shared the Chrome tab. What a boon. See, I actually noticed this time. I'm like, why is the other screen? Okay, we did tab. Boom. We just need window. Okay. Here we go. All right, the Planck units, yada yada. Link's a little doobly-doo for anyone that wants to look at it. Let's just go down to where are we? What do we want to do? Let's do okay. Let's just do the quick Planck scale. The term Planck scale refers to quantities of space, time, energy, and other units that are similar in magnitude to corresponding Planck units. This region may be characterized by particle energies of around 10 to the 19 gigaelectron volts or 10 to the 9 joule time intervals, or time intervals around 10 to the negative 43 seconds, and lengths around 10 to the negative 35. That's Planck length that we're talking about, and approximately the energy equivalent of the Planck mass. The Planck mass, the Planck time, and the Planck length, respectively. The Planck scale, the predictions of standard model quantum field theory and general relativity are not expected to apply, and quantum effects of gravity are expected to dominate. The best known example is represented by the condition in the first 10 to the negative 43 seconds of the universe after the Big Bang, approximately 13.8 billion years ago. Okay. But, okay, here's the actual part that I want to do. The four universal constants, by that definition, have a numeric value of 1. Expressed in these units are the speed of light in a vacuum, c, the gravitational constant, big G, the reduced Planck's constant, h bar, and the Boltzmann constant, k sub b. Yeah, you add in the Coulomb's constant, you can get the Planck charge and stuff. Okay, that's cool. What's the actual construction? Okay, Planck length, L sub b. It's the square root of h bar, Planck, that's reduced Planck's constant, times big G, divided by c, the speed of light raised to the third. Huh. Yesterday, it was the speed of light raised to the fifth for the Planck time. This is 3. Oh, very neat. Okay, and we go over to NIST. Here are the numbers we're looking for. The numerical value we're looking for is 1.616255 times 10 to the negative 35 meters. Okay. We get the error bars of 18. So those last two digits that could go up by 1 or down by 1. They go up or down by 8. So technically you can go a wee bit more there, it looks like. Okay. So what are we going to use to figure this out? Okay. We put in the thing exactly like we did in the book. Okay. So got our hyperbolic sine times the hyperbolic sine. 1 over the break-in scale symmetry, which is the 7 there. We raise it to the negative 1. And we multiply it by e, the base of natural logarithms, raised to the magnitude we're looking for. We set that as x. And we set that equal to the number of derangements we had, which was the break-in scale symmetry, which is those 7 circles, times the 5-dimensional ingredients we have that we're playing with: time, space, charge, mass, temperature. So we input that. Oh, look at how pretty that is. It's e to the x times a sine, hyperbolic sine, 1/7. Sometimes like, okay, it gives us this. The e raised to the x. I believe that's the cosecant of the hyperbolic sine, 1/7 equals 35. Okay. I mean that's not taking up a whole page. I mean there seems to be a lot going on there. Again, geometry really wasn't my major thing, and now I'm starting to learn it again. It's funny how that all works. Intergalactic planetary. That was a good song. But all right, we'll continue on here. So alternate forms. You can see. Oh, look, that's kind of pretty. Divide by 2 over 2. Oh, to the 35. To the 30. Look at all those 7s and everything. To the 7th power. This is very pretty. Okay. So what are we looking for? Looking for a real. Oh yeah. When you look at these numbers here, that's basically I to basically that 6.28 there. That's basically 2 pi. So basically, if you're going to do a rotation, which is 2 pi, basically a lot of time in physics and stuff like that, you'd see like 2 pi ki yada yada yada. Basically, this is what we're, or at least to the best of my knowledge, I'm going to claim. Because before, one of the questions, and it's a good question, was one of my questions, like before the last one we had 10 to the negative 44. It's like, all right, we got the magnitude. That's why I put in the comments, it's like the magnitude. Because one of the assumptions of the model is that basically, yeah, these are closed forms, but the number of derangements are set equal to the actual power that we're looking for. So basically, that negative 44, we're taking that 44 and we're literally assuming those number of derangements are the actual magnitude there. And then where's the 10 come from? It seems very simple. It kind of still creeps me out, but it's like, well, if you have 5 ingredients, you're dealing with a double covered geometric object. Okay, 2 covers, 5 ingredients. That's 10. 10 raised to that magnitude. I mean, it seems completely crazy. So again, either I'm just a madman on the internet, and I am a crazy person. That's totally true. So could be completely wrong. If it's not, I think that'd be pretty freaking sweet. Same thing over here. So basically, our right-hand side, we're assuming these derangements, that action would actually be the power that we are deriving here. That's essentially the claim. Okay. Could be right, could be wrong. If it's wrong, I'd like to find out, but seems to be doing pretty well. That's one of the reasons why we need to calculate the constants of nature, go through chemistry and everything. When we get through the periodic table, things are lining up in a coherent way and we're noticing patterns. Some may say some continents, if you would, that seem to have similar geometric actions under this construction we're using. That helps give the model strength. Because otherwise, it's like, here's just some numbers. Does it match experiment? Right now, we're at 2 more confirmed predictions in string theory. Muon G2 and the classical electron radius. They redid SI and got more precise. And then we found something even cooler. But yeah, hey, Mr. Quinn, thank you for joining. Here's the thing: 42 explains a lot. 44 explains more, I claim. Okay, but aside from all that, yeah. So number we get here is this. So what is the number that we're looking for? Number we're looking for is 1.616. 1.616. 255. 259. Wrong. Yes. Now, it might be wrong, but it still might be right. Why is that? Because we have our error bars here. So that could actually, that 255 could be a 256. It could be, actually, it's almost got a full point to it. So it could almost swing 2 in either direction. But, my friends, this appears to be a geometric derivation of the Planck length. Or at least that's what I'm willing to claim, because at least playing around with it, just seeing this is like, whatever. You spend enough time, it's like, model is a lot smarter than I am. Even a noob like me could start to explore the computational universe and start to gain a wee bit of a semblance, I'll claim, of what might actually be going on. Could be wrong, but again, if it's not wrong, how very fascinating. But that's always, hey, welcome Ernesto. Good to see you, my friend. Good to see you. But it's that's a good question. I don't know. Uh We'll have to see. I occasionally think about that, but I'm gonna say that let's just go with energy must be conserved. That's my cop out for that one. As far as gravitational waves go, again, not a professionally trained physicist. Do it on the internet. That's been fascinated. It's also been blessed to talk with some really smart folks, including some of the folks that are probably watching right now or temporarily in the future. But that's all we got for right now. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but I think the good stuff is coming sooner rather than later. Peace out.